Hello and welcome to JEM 123, the Intro to Computer-Aided Design for Mechatronics. I am Neil Rosenberg, your instructor. Before we get going, students should confirm that they can go up to Moodle, log in, find the course, and please do take a moment to scan through the various links that are provided. You'll find worksheets, video presentations, all of your quizzes, your grades, contact information, and a lot more up there. There is no textbook, so everything you'll need is presented via Moodle. One of the things you'll find there is the syllabus. This has the grading information, contact information. Our objective for you for this course is you will gain experience with design, taking ideas, concepts, inventions, mechanisms, products, through the design process using CAD and end up with something that can be made that solves a particular problem. Using CAD, you'll create virtual models, you'll create assemblies, and the drawings which form the documentation for your designs. You'll become familiar with SolidWorks, how you can very quickly create very complex parts and assemblies in there, and then take them through to 2D drawings that tell other people about your design intent. As part of this, you'll learn about tolerances, how things fit together, how you can, through controlling tolerances, make sure that fabricated parts work together. And we'll talk about some of the simple mathematical methods of doing that process. We'll also discuss briefly some of the fabrication processes, what the materials are that they use, and what kind of tolerances you can expect. You'll also learn about the value of good documentation and what are the rules of documentation. When we do a good document, it provides a means for sharing information with others that will avoid confusion and create clarity. This can be really important once you get out into the commercial world. Things about this course you should know. This is clearly more work than your average one-unit class. As I mentioned, there is no textbook, so you are expected to attend all of the lectures. Please plan on arriving on time. Come a few minutes early if you can. I plan to get going promptly. If you arrive late, you're going to miss something. Check out the syllabus for the attendance policy. It can affect your grade. You are encouraged to use your personal laptop to run SolidWorks. This will allow you to do the work outside of class. We'll do our best to help you get it loaded on your machine, but don't expect us to do it for you. If you really run into a snag, you may end up either using the lab computers for the term or going over to IT services for UNCA. Maybe they can help you get it loaded. There is no licensing cost for using SolidWorks on your personal machine. This is a pretty big class. It's over 70 students. In order for us to keep things moving and well controlled, we've automated some aspects of the grading process. The quizzes are automatically graded. We use rubrics very heavily. We encourage you to keep an eye on your grades in Moodle so that you know that you're getting full and proper credit for everything you've turned in. We do our best, but we're only human, so if you see an error, please let us know. Lastly, this is a class in which you're learning a skill that you're not going to get it if all you ever do is class time work. You need to practice it. It's like learning an instrument. You need to do it and do it some more and then do it some more beyond that. Try different things. Pick up a part, reverse engineer it, grab a caliper, try to make something that you've wanted all along, and just kind of spend some time getting to know the tool. In this course, we're going to start out with you doing a quick hand sketching exercise. It'll be 4 orthographic views. We'll talk about that in a moment. And then once we get into the second week, and you'll actually see me in lecture, we get into a pattern of lecture and lab each week For each week there'll be a worksheet and a quiz, and this will carry throughout until we get maybe half or 2/3 of the way through it, at which point you'll get the term project. We'll continue the worksheets and quizzes to somewhat lesser extent. You'll be given some time in lab for your project, but please, in order to do it well, you will be doing some work outside of class time to get the project done. You'll enjoy the project, I think. We're going to be doing the puzzle box again. Each year it gets a little bit more interesting. You'll be actually creating the working product. We provide through our 3D printing lab the notion that you can actually create your parts, check that they work. You'll get 1 or 2 tries. You get a couple of tries at it. So there is no cost for it. So give yourself some time, get it right, and then at the very end, your final, there's no final exam. Your final is you get up and show us what you made and talk about how you've met the requirements of the thing. So CAD itself. Why do we use CAD? Computer-aided design. Notice it's not computer-aided. It's computer-aided. You are the thinking. You are the brain. This is a toaster. It's a means to an end. It allows you, once you have a facility for the CAD product, you can go very quickly from a thing in your mind to a built and tested part. It's unprecedented how quickly you can do that now with things like 3D printing. Whereas, in the bad old world, we used to wait weeks and months between drawing something on a drafting table and having an actual part in our hand to look at. If there are changes, oh boy, it can be really difficult. In CAD, you can change things very, very quickly, particularly if you've used parametric relations between parts. If you change a part that other parts rely on, if you've done the job well, you change the one and the others ripple through, and the changes just happen automatically, and they're visual, and boy, I mean, it's so fast. There's nothing like it, nothing in the manual world to compare. You'll be able to check for errors. You'll look for interferences. You'll look for, can this thing actually be built? Can I put the motor in? Can I put the fasteners in? Do things run into each other? You can do animations that show how complex mechanisms work, and you can prove to yourself that they function and move in a manner that you expect. And then we get down to sharing the designs with others. Well, you don't live in a vacuum. Everybody works as part of a team now. You have co-workers, you have your stakeholders or your management you'll be doing presentations to, vendors you want to communicate with, and finally the inspectors who will want to check a part once it's been fabricated. When you do your designs with CAD, you now have a durable record. It's not, it's not ephemeral. You can print it out, you can save it, you can archive it. You have proof of what you did and when you did it, in very fine detail. You must know that, maybe it wasn't so true 10 or 20 or more years ago, but now if you go to a job interview, particularly for an engineering position, they're going to ask you, what CAD package do you use? What are you good at? And if your answer is, well, I don't really know CAD, you're not going to get that job. So consider this as a necessary link in your chain of development. And of course, as part of this course, you'll be gaining experience, good experience, and not just sketchy. You'll be gaining some in-depth knowledge of the tools that SolidWorks provides you as an engineer and developer. We'll talk about documentation briefly. It really is not a dry subject. Documentation can be a beautiful thing. It is your means of sharing your concepts, whether you're an entrepreneur or a developer or an inventor. You're sharing your concepts with others, and the better your documentation, the more effectively It's going to tell other people, let them clue them in into what are you doing, what are you thinking, and how wonderful it is, this design that you've created. When you're dealing with customers or management or marketing, if your documentation is clear and unambiguous, it gives them an opportunity to tell you, we like it or we don't, or this is something we should change. And so if the documentation is not good or not present, they don't have that opportunity, and you might end up going way down the road and having a problem. Well, this is something, if you're doing documentation along the way and frequently having people, the stakeholders saying, yes, we agree, not only is it a way to avoid those critical failures, but it's a way for you to get their initial to say, look, you told me that it was good, and that's the direction we went. And you have it, in concrete, you have it for real. When you're dealing with vendors and IP or intellectual property professionals or patent attorneys or patent judges, the documentation can form the center, the heart of your claim to ownership of a particular design or invention. If it's good documentation, clear, and presents what you're doing well, then it becomes a more effective baseline for example, your patent or your IP claim. When you're dealing with a vendor, if the documentation is clear and unambiguous, then the vendor has to make it according to the documentation, and if they don't, you have a clear, again, an unambiguous way of saying you didn't make what I wanted, or you did make what I wanted, whichever way it goes. Once your product is finished in design or approaching finishing, the people who are creating user documentation, technical training manuals, marketing materials, I guarantee they're going to be camping out in your office saying, oh, I love that screenshot. I love that screenshot. Can you show a cutaway view? Can you show me an exploded view? And all of these things are readily doable within the SolidWorks context. If you're working in a company where they have document revision control management, then basically as you make changes or as your group evolves a product, you keep a record of the evolution of the product. You keep individual changes as they occur, and you can easily get back to prior versions if you need to. This is something that SolidWorks can provide a core of. Now let's talk about some of the nouns, some of the things that we actually use and do. In SolidWorks we create parts. Well, of course, this is the heart, this is the finest granularity of what you're working on is the individual part. It's something that can be fabricated, and it forms the basis for assemblies. Now an assembly can be a collection of parts. It can also be a collection of assemblies and other parts, or any combination of the two. And when you're creating an assembly, you're mating things in such a way that they behave like the real parts would once they're received. Lastly, the documentation. In CAD you would use the drawing capability to create the user documentation, and there are any number of things, any number of reasons why you'd want to do this. You create a bill of materials to show what parts need to be ordered. You can do, as shown here, an exploded assembly, how things fit together, what the part numbers are, what some of the fits and tolerances are, the proper way that they are meant to be put together, or even the order of assembly. It shows the revision, who you are, the name of your company, other notes and legends. I mean, boy, this is the way that you tell the story of what you had in mind and how this thing is meant to be. Whereas if you go back and look at the virtual parts or even the assembly files, they may imply what you want, but the drawing, the documentation, that is your way to put in, plain old text. Here's what I want, and here's what you got to do. So when we're sharing with other people, we might share the native SolidWorks files, but more often we're dealing with people, others who don't have SolidWorks or don't even want the SolidWorks files. We may give them an animation as shown here. We may create an STL file or stereolithography file that can be directly 3D printed. By the way, the STL files, if you look closely at this, is composed of many, many, many interconnected triangles that, when averaged, form the shape of the part that you're making. There are other formats. There's STEP, IGES, DWG, OBJ, and so on. These different formats are provided so that if you're using a particular CAD product and want to share a file with someone who's using a different kind of CAD program, but one that doesn't understand your native format, this is the universal donor. So if you give them a STEP file or an IGES file, they can then read it into their CAD program. They might not be able to recreate all of your extrusions and all the different steps, but at least they'll have the fundamental part that they can use. And you know, as I mentioned, many of the programs, if you take like Inventor or Fusion 360 or SolidWorks and others, each has their own native formats, and they're not particularly, they're a bit user grouchy. They don't share files, native files, particularly well, so we share them through these universal formats. So let's get down to it. Let's actually look at some parts. Let's do a little work and get you ready for the lab this week. Here's a sample part shown in isometric form. Isometric is a particular way of looking at the corner. Notice that there's no perspective in an isometric. It does not shrink as you get further away. It's just very flat representation. When we're doing a drawing like a sketch, we might, if we're skilled, we might draw isometrics as shown here. We might also want to show what's called orthographic views, and those are your front, left, right, top, bottom, rear, and so on, the various views. And here we're going to work on the front view initially. Imagine if you held that part where the front, as shown here, is facing you squarely and there's no perspective. So it would be very simple. In fact, in this exercise, you're not even going to show hidden lines or anything fancy, no center lines, just the object lines, the outside edges of each of the details. So imagine, just before I click to the next slide, what would this look like? Try to imagine what it would look like if viewed from the front. Well, it's a pretty simple part. Let's go. Here's a front view. It's shown right here. You see where, I don't know if you can see my mouse, but there's the front view right there. Notice all that you see are object lines, single lines. There's no shading. And so think, could you make this part? If all you had was that front view, would you know how to make it? Obviously the answer is no. You don't know enough. We need to add other views, and we use third angle projection. We'll talk about that in class, what it means. That puts the right hand view on the right, shown like this. Now we're starting to learn a little bit more about the part. Again, look at the isometric and get comfortable with how this represents what you would see if you were looking at the right hand view. We'll do a left hand view. On the left hand, it's very simple. There's no real detail. The top view, you can see the cutaway, the hole, as a true circle. Very important, particularly for this lab, but going forward in your documentation, the layout and alignment of the views must follow this standard. The front should be the middle front view, left on the left, right on the right, and top, and so on. If I had another view, you'll see where those would go. The point is, though, that they are aligned with each other. They're well spaced out. Now, you don't put the words, when you're drawing it, you don't say top, left, front, right, because it's assumed that is the standard by which we work. So the front would be where this is shown, and so on. You can take away views. You might not even want to have that left view because it does not add much information. If you had a part where the bottom has details on it that you wouldn't see in these 3 or 4 views, you may add a bottom view or a rear view. Anyway, in your first lab, you're going to create a 4-view orthographic illustration by hand. You're sketching it by hand. No tools, no CAD. We're going to provide the paper and pencil. We'll give you the part to look at, and we even show you which is the front of the part. Please do go up to Moodle and download the worksheet. There's a link in this spreadsheet, in this slideshow. There's also a link on Moodle to the worksheet. In the first lab, you're also encouraged, if you want to, bring your laptop and you can start downloading and installing SolidWorks while you're working on the lab. Keep in mind that our TAs are not paid IT professionals, and if you need additional help loading SolidWorks, they'll try, but if they can't get it done, go over to IT services. Now, before we finish up, I want to click over to Moodle very briefly and show you what Moodle looks like. Here we are. I've already logged in. Here's the Joint Engineering 123. Notice it says contact information. We'll scroll down a little bit further, and then we get into the week by week by week, and it tells you what the lecture is about. There are links here. There's a link to, in fact, the slide deck that I've been showing you right now. There's videos. Here's a video how to load SolidWorks and a supporting document. How to configure the menus. We'll talk about why that's important at a later date. And then finally, here's the worksheet for Lab 1. You will hand that in at the end. You'll be able to look here to see what the due date is. That has not been set yet. In addition, up at the top, here's a link to the course syllabus. You are encouraged to take a look at that. So that's about it. We hope you enjoy the class. Please do attend your lab, and if you have any questions or concerns, please bring them immediately to the attention of your TA or to myself. And again, you'll find my contact information in Moodle. And I wish you good designs, and hope you have some fun with this. Thank you for watching. This presentation is part of a series by Neil Rosenberg. Additional videos may be found on my channel at youtube.com.